Hello and welcome to lesson number 8, magnetic effect of a current. Keywords for this lesson are magnets, north, south, attraction, repulsion and induce. The key question for this lesson is, how do you make an electromagnet? Have a go at the first knowledge check. When you've completed the first knowledge check, come back and we'll check the answers together. Welcome back. Let's check the answers to the first knowledge check. Question number 1, name the 3 magnetic materials, iron, nickel and cobalt. Question number 2, why is steel also magnetic? It contains iron. Question number 3, how many poles has a magnet got? It's got 2 poles. Question number 4, what happens when you bring the north pole close to a south pole? It repels. What happens when you bring a south pole close to a south pole? It repels. What happens when you bring the north pole close to a south pole? It attracts. Question number 7, what direction do magnetic field lines travel? North to south. Question number 8, what direction will a magnet settle if free to rotate? In the direction of the Earth's magnetic field. Check your answers, give yourself a score on the side here, correct any you've got wrong. Overview for this lesson. By the end of this lesson you should be able to describe the magnetic effect of a current and construct an electromagnet. Now, just before we begin, I'm just going to remind you of some basics of magnets. So a basic magnet has 2 poles, a north pole and a south pole. When we bring 2 south poles together, they will repel. When we bring a north pole next to a north pole, they will also repel. So like poles repel. When we bring opposite poles, doesn't matter if it's a north or a south, together, they will attract. A magnetic field exists around a magnet, and we can draw that with field lines, and these field lines go from north to south. They are strongest near the poles, so we have 2 poles and the ends are the poles, and this is where the magnetic field strength is the strongest. And you can tell that from this diagram because that's where the concentration of lines is greatest. So again, this is a non-contact force as well. So you have contact forces and non-contacts. Magnetic force is non-contact, so it's a non-contact force. Magnetic materials include iron, cobalt and nickel. There is various other ones, but these are the 3 main ones you need to know. You also have other materials like steel, and steel contains iron, so that's why steel is magnetic. But sometimes in questions they ask you name the elements, and if they ask you to name the elements, you have to name these, because steel is an alloy, so it's a mixture. Also, this is a permanent magnet as well, so it's permanently on. You can't switch it off. Watch the video quickly and then we'll be able to answer these questions on whether or not magnets attract or repel. So, magnetism, attraction and repulsion. So, we've done this before as well, so after watching the video, let's fill in the table. North and north poles repel. South and north attract. And south repel. So like poles repel, and like poles attract. Now when we come back to the laboratory, we'll try this practical out. So the magnetic effect of a current. So what we're going to do in this demo will be pass a current through a thick copper wire, and you will have a perspex sheet or a sheet of cardboard. So you will have your sheet of cardboard, and you will have a thick copper wire going through that cardboard. And we're going to put a current through the wire. So we're going to connect that to a power supply. We're going to switch it on. We're going to have some little plotting compasses, and plotting compasses are just small compasses with needles. And we're going to pass a current through the wire by switching it on. And we're going to see what happens with the plotting compasses. We can also do it with iron filings. You can also drop iron filings on this piece of cardboard or perspex, give it a tap, and you will see that this wire will develop field lines. So again here, plotting compasses here. So plotting compasses. And the reason they're called plotting compasses are used to plot magnetic fields. Because the compass is magnetic, as soon as you put it near another magnetic field, the needle will move. So they're placed around the wire on the perspex sheet or piece of cardboard. And then you can use, once you put a current in, you can use the needles to plot the actual field line around the wire. So watch the video and we'll come back and fill in the table.
I have a wire that goes through a piece of cardboard here, and I've got it surrounded by little tiny compasses. They're all pointing generally this direction. And I'm going to run current through the wire that will be coming up the wire this way from underneath. So based on the right-hand rule, there should be a magnetic field around this wire. In which direction? Let's find out. So I'm going to clip this on now. So it looks like all of the arrows are tending to go around in a counterclockwise fashion from this perspective. Turn the current back off. Now I'm going to reverse the current and run it the other direction. So in this case, the current will be flowing down the wire through the cardboard. And let's see what direction the field is there. And now they all seem to be pointing in a clockwise fashion around the wire. The farther I get from the wire, the weaker the field seems to get. I didn't quite line up as quickly or prominently. I'll pull them back a little farther. So they're all being influenced by the Earth's magnetic field there. And they're not all pointing perpendicular to the wire anymore. They're being more greatly influenced by the Earth's field. This one was having a real hard time deciding, is the Earth's field stronger or is this one stronger due to the wire? Let's do a little farther out. There we are. One more try. Kind of a tepid response from a few of them. This one ended up pointing that way. The Earth's field is pointing this way. The wire is trying to point the field that way. And I end up getting some sort of strange component that ends up pointing away from the wire. It's trying to hook around, but it's not doing a real good job. So the field strength drops off dramatically with distance. We'll have to determine mathematically if it drops off as 1 over r squared or 1 over r or some other relationship. But it's definitely stronger close to the wire. The magnetic field around a current carrying wire.
I have a piece of plastic through which I've drilled a hole, and then I took a wire and looped it through the hole 10 times. So I have 10 strands of the wire here flowing through this hole. So if I have 1 amp of current flowing in the wire, I will have essentially 10 amps that's flowing in a straight line through the hole in the plastic. I'm now going to sprinkle some iron filings onto the plastic. I will now apply a current, and I will have to tap the plastic to get the iron filings to move. And you can see how the iron filings have rotated to form circles around the wire, indicating the form of the magnetic field intensity generated by a current carrying wire.
So now that you've watched the video, you should be able to fill this in, and what you should have noticed is the plotting compasses. Align towards the direction of the magnetic field of the wire, which is circular. So we have our wire, and we have a magnetic field, circular magnetic field set around the wire. So if this is our wire, the magnetic field goes in this direction around the wire. This effect was discovered by a famous experiment carried out by Ørsted. To find out a little bit more about this, you can watch this video here. Electromagnets. A permanent magnet will attract a piece of iron. So a permanent magnet will attract a piece of iron. However, the magnetism cannot be switched off. Magnetism cannot be switched off or controlled. We can use a magnetic effect of an electric current to control magnetism. So there is a magnetic effect of an electric current, and we can control magnetism. An electromagnet is a coil of wire. So an electromagnet is a coil of wire wrapped around an iron core. The iron core increases the magnetic field strength. So the iron core increases the magnetic strength. The wire needs to be insulated to avoid a short circuit. So the wire is insulated to avoid a short circuit. When an electric current flows through the coil, so when an electric current flows through the coil, a magnetic field is induced in the coil of wire. This magnetizes the iron core, increasing the magnetic effect. So it magnetizes the iron core, increasing the magnetic effect. Watch a video on how we make a electromagnet.
Hey guys, it's Andy from Tinker Crate, and today I'm going to show you how to turn a normal iron nail into an electromagnet. Here's what you'll need: sandpaper, 21 gauge magnet wire, scissors, a large iron nail, alligator clips, AA battery pack, batteries, and some staples. Step 1. Take your large iron nail and your wire, wrap it around the nail at least 20 times. Magnet wire is just copper wire with a thin coating on top of it. Uncoated wire won't work. When you're done wrapping your wire, leave a little bit sticking out and cut it with your scissors. Now take your sandpaper and use it to scrape the coating off the wire. As you sand, you'll start to see the copper show through from underneath the coating. Keep sanding until all the red is gone. Once you're done, do the same on the other side. Next, let's hook up our alligator clips to our battery pack. Clip one of the alligator clips onto a wire end. Now we're ready to test our electromagnet. So first you need to take your staples, spread them out. To hook up your electromagnet, just attach the other alligator clip. Then bring the tip down close to the staples. Voila, an electromagnet. One thing to be careful of with your electromagnet, if you leave it hooked up, it's gonna get hot after a little while. So make sure you turn it off by unclipping your alligator clip. Yeah? Thanks for checking out the video. Check out our other ones and subscribe.
Now we'll also investigate electromagnets, and what we'll change is the variables that we will change are the voltage and also the number of coils, and we'll see how that affects. So we have these independent variables, the things that we change, independent variables, and these are our dependent variables, the things that we measure. So dependent variables, this is what we measure. And what we'll do is we'll write the results here. Okay, but for now I'm going to show you a video. Watch a video and come back and we'll fill in some results.
Electromagnet Lab. Introduction. In this experiment we are going to investigate the factors that affect the strength of an electromagnet.
Hypothesis. If we increase the number of coils, it will increase the strength of the electromagnet. If we increase the voltage in the wire, it will also increase the strength of the electromagnet.
These are materials that we use in this experiment. They are power supply, wire, paper clips, nails, and alligator clips. Procedure. First, prepare the material. Second, remove the outer part of the wire and cord the wire around the nail. Third, connect the alligator clips with the wire and turn on the power supply. Test if your experiment works.
This is our result.
Conclusion: the strength of the electromagnet depends on a number of coils. Evaluation: we should try other materials such as nails and needles. We need to coil the wire tighter.
These are our real-life examples: electric motors, generators, MRI machines, levitating toys, and consumer electronics.
Welcome back. Let's fill in some results from the video that we've just watched. So in the video there was two voltages, 2 volts and 5 volts, that were applied around 15 coils of wire, or 15 turns. And when we had 15 turns, you picked up 1 electromagnet at 2 volts, and as we increased the voltage we picked up 5 paper clips. We also had 2 arrangements of coils. One was 15 coils or turns, and the other was 30 turns. And what we noticed was that we picked up 1 paper clip and 6 paper clips. So describe the effect of increasing the current on the strength of the magnetic field. So the way we actually measured the strength of the magnetic field was the number of paper clips that were picked up. So strength is proportional to the number of paper clips picked up. So the stronger the field, the more paper clips you can pick up. So describe the effect of increasing the current on the strength of the magnetic field induced in the electromagnet. So what happened was, as we increased the current or voltage, which as you increase the current you also increase the voltage, as you increase the voltage you increase the current. As we increase the current or voltage, the magnetic field increased. So describe the effect of increasing the number of coils of wire on the strength of the magnetic field. As we increased the number of turns or numbers of coils, the magnetic field strength increased. And now we've just come across this word here, induced, and essentially that means that we actually have any magnetic field that we cause, and because we cause a magnetic field we can actually switch it on and off. So we can switch the magnetic field on and off by removing the current. So that's one advantage of a electromagnet. The other advantage is we can control the strength by either increasing the current or the number of coils. So we can make some very, very powerful electromagnets. So if you've ever been into a scrapyard or seen a scrapyard, they use electromagnets to pick up cars. The advantage of using an electromagnet rather than a permanent magnet is you can switch it off, pick up the car from one location and move it to another location. If you had a permanent magnet, it'd be permanently stuck to the magnet and be very difficult to remove the car. Now, uses of electromagnetism. So we mentioned the one use for electromagnetism, which is using it in cranes to pick up cars in scrap yards, but there is other uses as well. So you can watch this video here to learn more about the uses of electromagnetism. Now have a go at the last knowledge check. Once you've done that, come back, we'll check the answers together. Welcome back. Let's go through the last knowledge check. Question 1. Name two poles which are attracted to each other, north and south. Describe what a current carrying wire induces, a magnetic field. Identify the parts of an electromagnet. So you have a coil of wire, an iron core and a power supply. What is a plotting compass? Small compass used to plot magnetic field lines. Question number 5. What direction will a plotting compass point in the Earth's magnetic field? Towards the north pole, or you can say towards the Earth's magnetic field. Identify one thing that can increase the strength of a magnetic field. So you have a choice of either increase the number of turns of the coils or increase current. And if you picked one of them, you can pick the other one for question number 7. Name the fundamental force associated with magnets, and it's a magnetic, the electromagnetic force. So it's one of the 4 fundamental forces. Check your answers, give yourself a score on the side. If you've got any wrong, can you correct them? If you want to learn more about the electromagnetic force and the fundamental forces, you can watch this video here.